Welcome to Electron microscopes. In 1892, Hertz was the first person to pass electrons through a thin sheet of metal. Planck's contribution of the equation that shows the quantization of energy helped contribute to de Broglie's discovery of the de Broglie wavelength, which helped us to understand that objects with mass, such as particles, can have a wavelength. It had been known for some time that if you want to observe something, then the wavelength of the waves that you're using to do so will affect the resolution of the image. You're not able to see anything smaller than the wavelength of the light that you are using. And that's because we need the light to reflect off any object that we wish to observe. And if the object is too small, then the light simply diffracts around it and will not reflect back to the observer. Here we can see that if the object we wish to observe consists of very small particles, then we're going to need very short wavelengths in order to observe them. The larger the wavelength is, compared with the size of the particles we wish to observe, the more blurry the image becomes. Visible light has wavelengths between 380 nanometers up to approximately 700 nanometers. This would be purple light, and this would be red light. The smallest thing that we can see would be 380 nanometers across. But the diameter of an atom tends to be between 0.1 and 0.5 nanometers. So we are unable to resolve atoms using visible light. However, thanks to de Broglie, we understand that electrons also have a wavelength. And in the previous video, we learned how the acceleration voltage, V, can help us to calculate the de Broglie wavelength. So if we have an acceleration voltage of 20 kilovolts, then we can calculate the wavelength. This would give us a wavelength of 8.7 times 10 to the power of minus 12, which is 0.0087 nanometers. More than enough to resolve the diameter of an atom. It's known that if you have an area with a magnetic field, and you have electrons entering that region, electrons with a negative charge, then they will experience a force perpendicular to the direction of travel. And you can make them travel in a spiral shape. Bush used these ideas to write papers about how we can use this effect to make electromagnetic lenses. Lenses that would alter the direction of electrons and be able to converge them into a focus point. His work was purely theory, but it was taken up by Ruska, who with his PhD supervisor made the very first electron microscope. Their electron microscope used an electron gun which emitted electrons through the process of thermionic emission. The electrons were emitted in several directions. So they used a condenser lens to straighten the path of the electrons. The sample that they wished to analyse was placed in the path of the electrons, and it had to be very thin to allow the electrons to pass through. They then travelled through the objective lens after passing through the sample. The objective lens altered the path of the electrons to bring them to a focus. And finally, they passed through a projector lens which magnifies the image onto a fluorescent screen. Where the image can be viewed. Ruska and Knoll built their first electron microscope in 1931, and it became known as the transmission electron microscope. Or TEM. It used magnetic lenses to spiral the electrons into the correct alignment. One of the problems with this is that the focus point can suffer from something called spherical aberration. Which in a light microscope is usually corrected by using a diverging lens alongside a converging lens. Unfortunately, when you're using magnetic lenses, it is impossible to create a symmetrical diverging lens. And this limitation was pointed out by Scherzer in 1936. He predicted that there was a limit to the resolution that could be achieved using an electron microscope. Despite this, the work continued. Ruska spent most of the rest of his career trying to perfect the electron microscope, and Crew made several important updates to the technology. One of these updates was to get rid of thermionic emission as being the source of the electrons, and instead have the electrons be accelerated by a large voltage from a plate that had a very sharp point. And what this did is it reduced the angle that the electrons were given out at and made it a much more defined beam. This helped improve resolution. They also used cathode ray technology, the type of technology used in old-style televisions, to turn this fine beam into a scanner that could go left and right and up and down across the sample and build up the picture much more gradually. The first of these scanning electron microscopes was developed by von Arden in 1937, but unfortunately his prototype was destroyed during World War II. Albert Crew was eventually able to refine this technology and produce the first ever picture of atoms in 1970. Another type of electron microscope was also being developed around this time, and it used the technology of quantum tunneling. Quantum tunneling can be observed inside the Sun, where hydrogen nuclei are colliding to make helium nuclei. A hydrogen nucleus consists of a single proton, and in order to make a helium, two of these must collide and fuse together to make the nucleus of a helium, which consists of two protons. But in order to do so, they have to overcome the repulsive force and get close enough together so that the strong nuclear force takes over and they can fuse together into one. But the energy required to get that close and overcome that repulsive force is extremely high, too high. But when we model the behavior using the quantum tunneling effect, we find that the calculations come out to correctly predict the power output from the sun, so that we know this must be happening. All particles have an associated waveform, and we know that where that waveform has a non-zero value, that particle may be found at that location. If there is a barrier in the way, then the probability of that particle existing on the other side of the barrier is not actually zero. And that's because the waveform is able to penetrate the barrier and exist on the other side. So we can see that on the left side of the barrier, the probability of finding the particle is quite high. The amplitude of the wave function is quite high. On the other side of the barrier, the amplitude of the wave function is much smaller, but not zero. And this means that if we measure the position of a particle, at any moment it might be on the left side of the barrier, or it might be on the other side of the barrier. But the chances of this happening are much, much smaller and will be a very small percentage. But if you have a large enough collection of particles, then this will be happening at a predictable rate. And this is how, inside the sun, protons are able to fuse together to form helium nuclei and overcome that repulsive force. And they do so at a rate that is equal to the output of energy from the sun. Inside a scanning, tunneling electron microscope, or an STEM, we are observing the lumps, the bumps, and the valleys in the surface of a material by using a probe that comes close to the surface. And the probe itself consists of a single atom at its tip. And this probe moves across the surface. We can adjust its lateral position and also its vertical position. And what is happening is that between the tip of the probe and the surface of the material, electrons that are inside the material are able to jump across the gap into the tip of the probe through the process of quantum tunneling. And there are two ways that we can use this probe to take measurements of the surface. We can use the constant height mode, where the probe moves across the surface, maintaining the same height at all times. And what will happen is that when the probe is very, very close to the material, like it would be at this point here, the current from the electrons jumping across the gap will be very high. And that's because electrons are more easily able to jump a short gap than they would be able to jump a larger gap. So the amount of current that's received in the probe tells us about the height of the surface as it moves across. The other mode that we could use is the constant current mode. And that involves adjusting the height of the probe to maintain the current as we go across the surface. And the height of the probe tells us about the height of the lumps and the bumps in the surface of the material. So a scanning tunneling electron microscope tells us about the surface of a material, whereas a transmission electron microscope tells us about the internal structure of the material. In the transmission electron microscope, the electrons need to be travelling as fast as possible, because the faster they travel, the shorter their wavelength, and that gives us the highest resolving power that we can get. When they pass through the sample, they can be slowed down, which increases their wavelength and affects the ability to have a high resolution picture. It can also affect the angle through which they are deflected when they move through the magnetic lenses. This causes the focus to be more spread out and can create a blurry image when it's projected on the screen. The scanning tunneling electron microscope doesn't have this problem, but then the electrons are not passing through the material and making a picture. The electrons are moving across the gap between the surface and the probe and giving information about the surface of the material only. This is a transmission electron microscope simulator. It's an online tool that allows scientists to practice before they use the real thing. Let me walk you through the most relevant steps. So you would choose a sample and put it into the specimen holder. So after placing the sample and inserting it, we would then need to evacuate the chamber. The sample gets moved into position, ready for the electrons to be transmitted through it. We can choose the different acceleration voltages and turn on the beam. Here we can see that the beam is being emitted from the electron gun and it being turned into a uniform beam by the condenser lens. It passes through the sample, and then the objective lens brings that to a focus to create the image. There are several other lenses in this simulator because this is a modern electron microscope. The projector lens is what magnifies the image onto the screen at the bottom. Once we've adjusted all the settings for the different lenses, we can start looking at the magnification of our image. At the minute, this is set to low. As you want to zoom in, you need to adjust the center point of your image. Very similar to how you would do this in a real microscope. You start off on the low magnification settings and then zoom in. When the magnification is at its highest, you can see the images of the individual atoms. This simulator is for the scanning tunneling electron microscope. Here you can see the probe, and here you can see the sample. The probe will come very close to the sample and scan up and down, left and right, visualizing the surface. In this simulator, it gives you several warnings about the probe and the sample coming into contact. This can cause damage either to the probe, sample, or both. As it starts scanning the surface, the image starts to appear. And in this simulation, you can adjust the different settings to get different zoom values. This kind of a simulation allows researchers to practice using the skills that they're going to need when they're using the real thing.